Hello and welcome to this presentation on applying calculus to real-world situations. So what we're going to do is we're going to see how calculus, or in this particular situation, how differentiation can be applied to make a task easy. So this is what we do in engineering and science. We use the maths that we use it to make life easier. We use it as a tool. Okay, it's part of our toolbox. So what we've got here is we've got three common equations. You're probably familiar with these. If you've done physics, you will have seen these. So we've got v is final velocity, u is initial velocity, a is acceleration, t is time. In this example, we've got displacement s, so that means distance that you've travelled. So if you go from A to B, you've obviously travelled, so that's the distance. So in physics, we tend to use the letter S for displacement. So there's another formula there, and then the third one is also gives us the velocity, but in this case we don't know time, but we know how far we've travelled. So that's the purpose of it. There's a few criteria required here. The acceleration has to be constant, and motion should be in one direction, just about. I mean, we can sort of generalize things a little bit and still use these formulas, particularly on the thing to do with direction. Okay, now with differentiation, interesting thing is here that if we've got displacement and we differentiate it in relation to time, that will actually give us the velocity. So what that's saying is if we differentiate the displacement, the gradient it finds is equivalent to the velocity. Now the interesting thing there is that then if you differentiate that velocity, the answer to the question, the gradient, is equal to the acceleration. This here is another way of writing the same thing, because if you think about this, really what you've done is you've differentiated once, found velocity, differentiated again, and you found acceleration. And this is saying you've differentiated the initial one, the displacement, twice. So if you see this terminology, don't be alarmed. It's just a way of writing it. It's actually an easy way. It's actually easier usually to do a double differentiation, because the second one's usually got less terms left in it, as you'll see when you do some examples. So it's usually not anything to be alarmed of. In theory, you can differentiate a third time, a fourth time, a fifth time if you wish. Okay, so that's what it means, and the correct terminology is to say d2s over dt squared. That's the general grammar, not that important, but just for your information. Okay, right, so let's have a look what happens. So if I plot this, so if I make u equal to 10, so that'd be 10 meters per second, and I make the acceleration equal to 5, so that'd be 5 meters per second squared. Put them into my sum here, my equation, plot them, I'll get this. If I do it from up to 10 seconds, so I get this, and what I'm getting here is I'm getting a bend, because the distance travelled, the displacement, increases as a speed increases. So as you apply the acceleration, you make the speed increase. So obviously if you're going faster, you cover the greater distance in a second. Very logical. Of course, maths is always logical, and this is very logical. So that's what we've straightforward. So what we can do with this, having got our graph, or having got some figures in a table, what we can do is we can use, if we want to say find the gradient at 6, we could do our rise over our run. If we put a line on here, the best fit. Let's see if, like this kind of thing, like you've done before, to represent the gradient. Find that, put a little triangle on if you've ever done it this way. So what we're saying there is we're getting the difference in the rise, so the difference in the height gives us the rise, over the distance in the length gives us our run, so I rise over the run, do the maths, and we get the gradient. Okay, that works very well. But the point of this is to show it's a lot easier to differentiate it, especially if you get a difficult formula. This is a simple formula because acceleration is constant. if acceleration was squared or square rooted or both, not obviously both, but say 2/3 to a power of 2/3, something of that nature, then it would be very difficult to plot. If it was a combination of terms of a sine wave and an exponential and polynomials, then it would be even harder. So it gets tricky. You wouldn't really want to plot it all, especially when there's an easy method, and that is to differentiate. So let's have a look. So if we differentiate this term here, so let's have a look at that. So we're looking for v. So what we're saying is v equals the differentiation of displacement. So ds over dt, displacement against time. That's easy enough. The ut would just leave me with u. And then the other term, the 2, would come down to the front, multiplying to the half. So we'd have 2 halves, which is 1. So we just get left with at. Okay. Nice and easy. So if I want to know the gradient at 6, all I would do is put 6 into there. So I've got 10 here, 10 plus 5 times 6, and it'll give us the gradient. And the gradient is the velocity. Simple as that. Okay, if I look at the next slide, so there's a plot of it there. So there's a plot of this with those values for u and acceleration, and you'll see that this here, you'll notice that this follows our, that's not right, equals, but it obeys this rule for the straight line graph. Okay, so m's your gradient, x is your variable along the x-axis, and c is our c of constant there, which we happen to know u is 10, so that agrees with that. So it's nice and neat. Now if I go back up a couple of slides, we'll see that we've already got an expression for velocity, and it's agreeing. So the differentiation of this gives us this. So you see how all these things all work together, they all pull together, they're all tied in. It's the brilliance of maths. It always gives the right answer if you do the maths correctly. And these are the kind of things we call proofs, and proofs are what mathematicians require, physicists require, to prove that something is the way it is. That's the thing about maths, you can get proofs. In science we don't really ever have proofs, all we ever have is evidence that points to a certain way, and sometimes we don't even have the evidence, we don't have the empirical evidence, we've just got theories. But in maths they are proofs. So we can see how that all ties in. So we get this nice straight line. Okay, and as you can see, it's a lot easier to do the differentiation. Now here's a question for you. What happens if we differentiate again? So let's have a look. So I'll just go back up actually to my formula. Well, I can write it fresh on the new page. That's why I've got space. So we're now looking for the acceleration. At the minute we've got v equals u plus at, where u is 10 and a is 5. Now if I differentiate this again, okay, against time, which could have been written like this, double differentiation of our starting point, displacement. Okay, they're exactly the same. Then I'll get, so, and this is acceleration, so acceleration is equal to that, which is equal to that, so my acceleration is equal to, so u disappears because it's a constant, it's a to the t to the 1, so I just get left with a. So not surprisingly, the acceleration is equal to the acceleration. So if I plotted this, let's do a quick plot, what I would get in this one, so that's my y-axis, that's my x-axis, a is a, so whatever it is, so what I would get would be a straight line, like that, which would be 5. Okay, in our example. So And that's what we expect, because if we go back to our initial formulas, what have we got here? We've got this rule that acceleration is a constant, and we've just proved it. So nice and easy. Now again, in this is a simple example, simply applied. Some nice little proofs there of the formulas. But if we wanted, if we had a more difficult, complicated expression for velocity, because if you think about it, when you're talking about velocity of, say, a car, you've got lots of things coming into effect. You've got you put your foot on the accelerator if it's a petrol engine. You put your foot on the accelerator in first gear, it starts to move from 0. You've got the acceleration, you reach an optimum power point where it accelerates quicker, then it starts to tail off, then you change to the second gear, and then you go through the process again, and so on until you get to your top gear, whatever that bit may be, 4th or 5th gear, and then you eventually reach your maximum speed. Fighting against you all the time, you've got friction, you've got the friction of the wheels, you've got the airflow across the car. As you get faster, those frictions get greater. This is why you have a terminal velocity. I'm not referring to when you hit a wall in that point, that kind of terminal, but the car will reach a maximum speed at some point, because the air resistance, the forces of the air resistance will equal the force that's been applied from the engine. So you'll reach this final velocity. So you've got the formula is a lot more complicated, but the principles would be the same. So there's a classic example of how it helps. And of course, with that example I just gave about a car engine, the acceleration also changes, of course, and a double differentiation would give you the acceleration at any point in time. Okay, so I hope that's a good starting point for you on the applications of differentiation. And I'm going to do some more, there'll be some more videos to follow that will be going into a bit more depth. Okay, thank you for listening.